This video is all about matrices. We'll start with a little introduction, and then we'll go into matrix operations. A matrix is a square or rectangular array of numbers, so it's really just a way to hold numbers in places. We describe a matrix in terms of the number of rows it has, and then the number of columns it has, which go up and down. So if I call this matrix A, I would say that A is 4 by 4 because it has 4 rows and 4 columns. Again, rows go left to right, columns go up to down. One other thing we can do when we label a matrix this way, when we describe it this way, is we can pick out entries based on where they're located. So for example, this entry here, I might call the entry A22, as in the entry from matrix A that's in row 2, column 2. The row always comes first, the column comes second. So this one right here, I would call that A34, or another way to write it is entry 3, 4. So you might see entries described both this way or this way. Just remember that the first number is telling you about what row you're in, so that number's in the 1, 2, 3rd row, and the second number tells you about what column you're in, so it's in the 1, 2, 3, 4th column. What else can we do with matrices? We can describe them in a variety of different ways. So we can talk about matrices that are square in shape when they have the same number of rows as columns. This is a square matrix that I would call symmetric because if I folded it along the diagonal, the other entries would match up. Another way to say that is entry ij equals entry ji. If I flipped the rows and columns, I'd have the same matrix. And only a square matrix can be symmetric. This line down the middle that I identified in the last matrix is called the diagonal. And a matrix that has only numbers on its diagonal and zeros everywhere else is called a diagonal matrix. So you might hear that word used. If I have a diagonal matrix where all the entries on the diagonal are ones, this is called the identity matrix, sort of like the number 1 but in matrix form. And if every entry in my matrix, square or not square, whatever shape I want, but if all the entries are zeros, I call that a zero matrix. The first matrix operation we can do is called scalar multiplication. This is when we take a matrix and multiply it by a number. That number can be a positive number, a negative number, a fraction, a decimal. This is probably our easiest matrix operation. All we do for matrix multiplication is, for scalar multiplication, is we take our scalar, the number in front, and multiply it through to each and every entry in the matrix. And it doesn't matter what size or shape our matrix is, scalar multiplication always works. So 3 times the matrix shown there would be 3 times 4, 12, 3 times -5, -15, 3 times 0, 0, and 3 times 2, 6. My final answer with scalar multiplication is always the same size as the matrix I started with. This guy was 2 by 2. My final answer will also be 2 by 2. What's the next operation? Matrix addition or matrix subtraction. This is also a relatively simple style of matrix operation. We do it entry by entry. So, for example, if I want to add these first 2 matrices, I take the first 1, 1 entry in each and add them together to get the 1, 1 entry in the new matrix. So 0 plus 5, this would be a 5. Then -1 plus 6 gives me 5. 9 plus -9, or in other words 9 minus 9, gives me 0. And finally 10 plus 4 gives me 14. Notice that again, the size of the matrix I end up with is the same as the size of the matrices I started with, but this brings an important point into play for matrix addition and subtraction. This operation is only defined if our two matrices have exactly the same dimensions. They have to have exactly the same shape. So in these examples I'm showing here, all of my matrices are 2 by 2, so this will always work. But if I'm trying to add, say, a 2 by 2 matrix with a 3 by 2 matrix, I would say that that operation is not defined. Because if we're doing this entry by entry type of addition or subtraction, then we need the number of entries to match up in both. Let's do a subtraction exercise. So again, entry by entry. I've got two matrices that are both 2 by 2, so I know that this operation is defined. I can do it. I'll do 7 minus 5 is 2. 14 minus 2 is 12. 2 minus 2 is 0. And minus 3 minus 0 is negative 3. I could call up just one of these entries. So for example, I could say, what is the 1 entry of 7, 14, 2 minus 3 minus 5, 2, 2, 0. So what is just this entry? And with matrix addition or subtraction, because it's entry by entry, I would identify the entry in row 2, column 1 of the first matrix, then row 2, column 1 of the second matrix, and I would subtract those two to give me the 2, 1 entry in the resulting matrix. So in other words, if I'm just asked for one entry, I don't have to do the whole matrix addition or subtraction. I can use a shortcut just to identify that one entry. Transpose is another thing that we do with matrices. Transpose means a flip. We flip the rows and the columns. So if our original matrix is 2 by 2, our transpose matrix will be 2 by 2. If our original matrix is 2 by 3, that would turn into a 3 by 2. The rows and columns flip. So we change dimensions if our matrix is not square. This matrix is square, 2 by 2, so even if we flip rows and columns, it'll still be 2 by 2. But it looks like this. So highlight the first row. That first row will now become your first column. The second row will now become your second column, and so on and so on and so on. So our first row, 1, 2, becomes our first column. Our second row, 3, 4, becomes our second column. And again, I could call up a single entry. If I said, what is the 1, 2 entry of the transpose equal to? Then I'm looking for the 2, 1 entry in the original. So row 2, column 1, that's a 3, and there it is in the 1, 2, row 1, column 2 position. So it equals 3. The last matrix operation is matrix multiplication. This is the most complex of all of the matrix operations. In order to do matrix multiplication, what we need is, if we write out the dimensions of the matrices side by side, so 2 by 2 and 2 by 2, we need those middle two numbers to match up. If they do, the operation will be defined. If they don't, the operation will be undefined. And the size of our result will be the numbers on the outside. So in this case, our result should be 2 by 2. The way that we do matrix multiplication is in an across and down way, I say. So we work with each row. We go across the row and down the column. Then we go across the row and down the next column. If there was another column, we'd go across the row and down the next column. And then we move on and we do the next row. So then we'll do the second row across the first column, then the second row across the second column, then the second row across the third column, and so on and so on and so on. So let me show you what this looks like. So our result will be 2 by 2. The first move I want to do is across the first row and down the first column. So I do 5 times 1 is 5, plus I always add when I take the next step. So the next step in my row is a 2, and the next step in my column is a 2. So 2 times 2 is 4. So that entry is going to be 5 plus 4. Then I move on. I'm going to do the same row again, but this time with the second column. So 5 times minus 2 gives me minus 10. And 2 times 3 gives me 6. So I did the first entry in the row with the first entry in the column, then the second entry in the row with the second entry in the column. Then let's move on to our second row. So across and down, first entry in the row with first entry in the first column, 1 times 1 is 1. Then second entry in the row, second entry in the column. Minus 3 times 2 is minus 6. Then we'll do same row with the last column. So 1 times minus 2 is minus 2. And minus 3 times 3 is negative 9. So that leaves us with a matrix that looks like 9, minus 4, minus 5, and minus 2 plus minus 9 is negative 11. Again, I can call up a single entry. So if I said, let's find the 2, 2 entry, what is that equal to? I would take row 2 of the first matrix with column 2 of the second matrix, and I would do that across and down. So I would do 1 times minus 2 is minus 2, plus minus 3 times plus 3 is negative 9, and I'd end up with negative 11, which is exactly the entry I had in the 2, 2 position of my result. But if I'm just calling up one entry, I don't have to do the whole multiplication. I can just identify which row goes with which column. Let's look at another example of matrix multiplication, this time with matrices of different dimensions. So in the first one here, we have a matrix that has 2 rows and 1 column, 2 by 1. In the second one, we've got 2 rows and 2 columns. So if I write these out beside each other and line them up, I see that the middle 2 numbers don't match. So this result is undefined, or in other words, I can't do this multiplication. If we look at the second one and line up our dimensions, we've got a 2 by 2 next to a 2 by 1. This time when I put them this way, I can do the multiplication. The middle 2 numbers match up, and my result should be size 2 by 1, just like the first matrix there. So we'll go across and down. So across our first row, minus 3 times 1, plus 4 times 2 across and down. And then we use our second row and go across and down. So 0 times 1 is 0, plus 1 times 2 is 2. And our result looks like 5, 2, a 2 by 1 matrix. I hope that helped clear up some of the operations and definitions for matrices, and I will see you in the next video.